Hi, good morning everyone. I'm Sooraj. I'm a PhD student from the Indian Institute of Science. So today my talk is on a Super-Nernstian ISFET using scale Coplanar channels as we would see. So just to give a brief background, ISFET stands for Ion Sensitive Field Effect Transistor, and it's a solid state ion sensor which has this very similar architecture to conventional MOSFET, where the only difference is that you just change your metal with an electrolyte and you can use it to, with all the advantages of a conventional CMOS platform, you can use it to measure a very simple biomolecule, that is a pH, to any complicated with appropriate functionalization. And because it is based on the CMOS architecture, you have all these advantages: real-time, compact, low power, inexpensive, etc., etc., etc. And the way it works is very simple. If you have an oxide, it will be a pH sensor based on the dangling bonds on the surface, which is usually hydrated in the atmosphere. And if you have an acidic medium, then it gets protonated and you have an excess positive charge that is generated. And in case of an alkaline medium, you have this negative charge that is generated, and a MOSFET, or in this case ISFET being a charge sensitive device, you have this, you can sense this charge based on the how the transfer characteristic change. So if you have a device that has a transfer characteristic like this, the moment you introduce an acidic medium, it will protonate and left shift, and in an alkaline medium, it will deprotonate and it will right shift. And in this case, the sensitivity would be the shift in this gate voltage per unit pH, and this is the voltage sensitivity of an ISFET. And as we talk about the charge accumulation, the side binding theory, the moment you have this charge accumulation due to protonation and deprotonation, what happens is that you have these counter ions that are coming in and screening out these charges as shown here. And the statistics that is followed by these ions, the Boltzmann statistics, ensure that these distribute over a distance from the surface of this oxide, and with a potential developed and an electric double layer formed. And because of these statistics that is being followed, what happens is that the maximum potential that can develop at this surface, and consequently the maximum voltage sensitivity that you can measure with a single gated ISFET is limited to 59 millivolts per pH at the room temperature, and which is called the Nernst limit. Now immediately we have a problem, because this 59 millivolts is per a unit change in pH. And if you want to measure something like, say, a physiological solution, for example your blood, which has a pH that is varying from 7.3 to 7.4, you have only 0.1 decimal change. And in that case, this sensitivity is not adequate. So we need to figure out ways to extend the sensitivity beyond the Nernstian limit, and that is what the Super-Nernstian is all about. And how can we do that? So far, if we go from the single gated ISFET, where I introduce the electrolyte or the liquid solution to the same gate, if we decouple that to a multi-gated ISFET structure, where we have the sensing happening on one gate and the transduction happening with another gate with two different transconductance, then what you can do is you can introduce this gain factor, which is the ratio of these transconductances, and then you can have this amplification factor over the single gated sensitivity. In that way, you can achieve Super-Nernstian sensitivity. And conventionally, this is done by a very simple architecture where you have an asymmetric dielectric. So if you go with a double gated device, and you have a thin dielectric and a thick dielectric, and by just the virtue of the difference in gate oxide, you are able to have this gain factor. The problem is you cannot miniaturize them very easily, because the moment you have asymmetric structure, you are locked to a technology node. If you are going with a given technology node, then your top dielectric can only be so thin. So it is difficult to miniaturize. So to have a scalable, miniaturizable, highly integrated device structure, we need to have an architecture that is that is very easy to miniaturize. So we would like to go with a symmetric dielectric, and we would like to see how we can have scale devices in such a device architecture. And for that, what we propose is a coplanar multi-gated ISFET device as shown here, where what we do is we have very scaled ultra short channels of 50 to 200 nanometer that is used for the sensing purpose, and these are transduced against a longer channel length of 500 nanometer. Now, instead of using the different oxide thickness, here we are using the channel length to modulate the transconductance, which is inversely proportional to your gate length. And the structure is shown here, where you have very symmetric dielectric of aluminum oxide and ultra thin 10 nanometer, and we are using the very popular 2D material molybdenum disulfide as the channel. And you can see the coplanar channels. So this is 50, 80, 100, 200 and 500 nanometer, and only the 500 nanometer has a gate, top gate. This is the sensing gate, where we are measuring the sensitivity, and we have a fluid gate that is for giving the general reference bias to the electrolyte, and we also have a global backgate, because of course this is 2D, we can do that. And this is the top structure schematic of this device, where we are at this point we are connecting all these in parallel, the 50 to 200 nanometer. This is one device architecture. We can always mix and match to get the maximum sensitivity that is needed. and here we have the top gate. And this is an equivalent circuit of our device structure where we have this sensing gates all in parallel sensing the electrolyte pH, and transducing gate of 500 nanometer VTG that is used to transduce against and get the sensitivity. And we also have a global back gate that gives a global control over all these. And this is the small signal equivalent equation. And here, if you modulate all these different transconductance, we will be able to modulate and change our sensitivity to whatever we need. And to fabricate this device structure, we exfoliated fuel air MOS2 on 10 nanometer of Al2O3 on silicon. And then we fabricated using electron beam lithography and a lot of software algorithm for proximity correction. We were able to get this very narrow 50 nanometer gap. And this is a SEM image of the fabricated device structure with all these coplanar channels. And then we have the top dielectric, again ALD, aluminum oxide, annealing, all those interface controlling procedures. And we have top gate fabricated by EP lithography and nickel. So this is our final fabricated device, the electron microscope image of that, where you can see all these channels, the shorter channels are exposed to electrolyte, this longer channel is insulated from it, and that is being used to transduce against. And with that device fabricated, if you measure the electrical response in dry, what we get is a very typical response from a MOSFET device, where we can see the transfer characteristic as shown here. The on-off ratio is not very great, but that is not really important for ISFET device. And if we see the characteristic of the coplanar top gate, this is interesting. Here we see that we need a gate control, but we need very minimal gate control. That is the entire purpose of how we can gain sensitivity with this architecture. And here we are getting that we have a very minimal control, but there is definitely a control with the coplanar top gate. And this is when all the other gates are biased to 0 or floating. And if you also measure the transconductance, which is where all this argument is coming from, with an electrolyte, so that we can measure the transconductance of the fluid gate as well, we see that the fluid gate has the maximum transconductance, which is way higher than either the coplanar top gate as well as the global back gate. And this is because of our interface engineering between the back aluminum oxide and MOS2 interface, as well as the top aluminum oxide and MOS2 interface, indicating that by modulating the interfaces as well as by playing with the channel lengths, we are able to get a control over this transconductance without going with an asymmetric or non-scalable kind of device architecture. So with this transconductance characteristic, we should be able to get a sensitivity that is way beyond the Nernst limit. And this is what we will be seeing in the next slide. So with that, we went ahead and measured the wet electrical characteristic of this device in the presence of pH. And we use pH of 6 to 8 using phosphate buffered saline, which is the common, very popular practice. And for that, we have this. We initially started with the fluid gate. So fluid gate is when we are measuring with the fluid gate, this is just like a single gated ISFET. So we don't expect very high sensitivity at this point. But you can see a clear right shifting characteristic with the fluid gate when we are connecting, keeping both the top gate as well as the back gate to 0, and for a wide range of pH from 6 to 8. And this clear right shift is visible here. And at this point, if we measure the voltage sensitivity by drawing a line like this, we get a very linear trend with a sensitivity that is 35.9, of course below the Nernstian limit. And the purpose is how the rest of our gate will help us to extend this sensitivity much beyond this limit. So with that, if we see the coplanar top gate, so this is when we are biasing the back gate as well as the fluid gate to 0 reference, and the fluid gate is an AGCL reference electrode, so that also doesn't shift the electrolyte potential. And here, if you see, from pH 6 to 8, we have a very clear right shift. And if you measure the sensitivity at this point by drawing a line again, it again shows a very linear trend with a sensitivity of 100.9. That is again almost double the Nernstian limit. So with this architecture, we are able to get a gain over the sensitivity. And right now we have just connected all the channels in parallel, and by further scaling as well as playing with the different connections, we should be able to get this sensitivity to any different sensitivity values that we need. We also measured this against the global back gate, which controls all the channels simultaneously. And since there is a difference in transconductance between these two, the fluid gate had higher transconductance than even the global back gate. So because of that, we should be able to get a high sensitivity even here. And that is exactly what we see here. If we go from pH 6 to 8, we see a clear right shift again with when the other two terminals are biased to 0. And here the sensitivity turns out to be even higher. It is around 246.9 millivolt per pH, which is around 5 times the Nernstian limit. So we are able to, the device is symmetric, and the aerial footprint is much smaller because of our gate length scaling. And with that, nevertheless, we are able to get a super-Nernstian sensitivity from 100.9 with the Coplanar structure and to 46.9 millivolts for the global gated device architecture, which is massive. And yeah, with that, what we have is a coplanar TLM like array of is for device with structure as shown here, which is able to show super-Nernstian sensitivity because of both our coplanar architecture of different channel lengths, as well as by the interfacial engineering between the both the top and bottom dielectric. And this remains symmetric and very scalable device architectures, which you can miniaturize and take it down to any different technology nodes that you want. And on future, of course, we have shown only with pH. We would like to take it further to other biomolecule sensing by functionalization, which is happening in parallel. And yeah, this is what we got with the fluid gate. Our sensitivity is below Nernstian. With the top gate as well as the back gate, we are getting beyond the Nernstian limit. And yeah, with that, I would like to conclude and thank my advisor, Professor Navakanta, and funding agencies and Sense Industrial Affiliate members. Thank you. Questions?